Okay, in this lecture we're going to finish our section 12.1 material on local extrema. So we had seen in our first part of this section that the derivative of a function can be used to determine intervals on which a function is increasing or decreasing. And we saw that the local extrema of a function would occur at critical points, which were points for which the derivative of our function is either equal to 0 or does not exist. And the last example that we had left off with was involving finding critical points of some functions. And those were the candidates for where we have our local extrema. So in this part of our section, we'll learn a method involving the first derivative to determine whether a critical point yields a local maximum, a local minimum, or neither. So this result is called the first derivative test. And it says that if c is a critical value of some continuous function f, then we have one of three cases. If f prime of x changes from a positive to a negative at the value c, where we have a critical value, then f has a local maximum at c. So let's illustrate that geometrically. So let's suppose that we have, maybe I can use just a number line here. So let's say that we have our number line, maybe representing the domain of our function, and we have a critical value at some point c, or at some value c. Now the first part of our first derivative test says if the sign of the derivative changes from positive to negative at c, then we have a maximum at that point. So let's think about that. If our derivative was positive to the left of c, that means our function is increasing. And if it changes to a negative at c, that means our function is decreasing to the right of c. So the graph of our function, we can see the way that we've illustrated it, has a peak or a maximum that's occurring at c itself, where we change from increasing to decreasing. So that is the first case for this first derivative test. Now, the second part says if the sign of the derivative, f prime of x, changes from negative to positive at c, then the function f has a local minimum at c. So again, to illustrate this, let's suppose that we have the x-axis for the domain of our function, and at some value, x equals c, we have a critical point. So if the sign of the derivative changes from f prime of x is negative to f prime of x is positive, that means that our function moved from a decreasing function to an increasing function at c. So based on the graph of our function, we can see that it appears to be bottoming out, or it has a minimum at this value c. Now the last case for this first derivative test says if the sign of f prime of x does not change at c, then the function does not have a local maximum nor a local minimum at c. So again, we could see that if we consider our x-axis and we have some value x equals c, and let's say that our sign doesn't change. Maybe we move from positive to positive, so the function is increasing to both sides of c, or perhaps decreasing, then we see that we do not have a maximum nor a minimum at c. All right. So let's look at some examples where we will combine determining the intervals of increase or decrease for a function, along with this first derivative test to determine where our function has its local maximum or minimum values. So in this first example, we have the function f of x is some polynomial, and in part A, we're supposed to find the intervals on which the function is increasing or decreasing. So to determine where a function is increasing or decreasing, we need to first find the critical values, which means that we look at our derivative, which is 3x squared minus 6x minus 24, and we ask ourselves, is there anywhere that it is undefined? In this case, no, since it's a polynomial. So the only values that we could have for critical values are values that would make this derivative equal to 0. Now, dividing both sides of our equation through by 3, we have x squared minus 2x minus 8 is equal to 0. And then this can be factored as x plus 2 times x minus 4 is equal to 0. So we're left with two critical values, namely x equal 2 and x equal to 4. So if we think about our domain of this function, in this case all real numbers, so the entire x-axis, we have these critical values at x equals -2 and +4. And to determine whether our function is increasing or decreasing on each of these subintervals, we need to determine the sign of the derivative by choosing a test value of x in each subinterval. So for instance, to the left of -2, I could use -3. And to determine the sign of the derivative, I could look at f of x, or in this case, f of x divided by 3, and I want to know if this product is positive or negative. So if x were -3, I would have -1 times -7, which would be a +7, so an increasing function on that interval. Now between -2 and +4, I could take x equals 0, and plugging in 0 to my derivative, I'm left with a -24, or after we've divided through by 3, a -8. But in any case, we see our derivative is negative, so our function is decreasing on that interval. And then to the right of 4, if we choose x equals to 5, we would have a 7 times 1, so a +7. We move back to an increasing function. So we see from inspection here that we change from increasing to decreasing at x equals -2. So we're going to have a maximum at that point. And we've changed from decreasing to increasing at 4. So we're going to have a minimum at that point. So for part A of this problem, to determine where our function is increasing or decreasing, let's state the following. Is this increasing on the interval -infinity to -2, or from 4 to infinity, and our function is decreasing on the interval from -2 to +4. So that was what we were asked in part A. And then in part B, using the first derivative test, we're told to find the local extrema of f. So those are the local maximum and minimum values of our function. So using the first derivative test, we saw in part A that our function changed from increasing to decreasing at -2. So that means that we have a local maximum at the value x equals -2. Now to find the local maximum value, I need to take -2 and plug it into my original function to see what the value of our function is there. So plugging in -2 to our original function that we're considering the graph of, we're left with a positive 33. And we have a local minimum at x equals to 4, because we saw from our part A work that we moved from a decreasing function to an increasing function at x equals 4. And to determine the local minimum value, we're going to substitute 4 in for x in our function. So substituting 4 in place of x, we're left with a negative 75. So here we have the location of these local maximum and minimum values at negative 2 and 4. And the maximum and minimum values themselves were 33 and negative 75. So let's look at some other ones. In our next example, we have the function f of x is x over x squared plus 1. So a rational function, a quotient of two polynomials. And we're asked to determine the intervals on which f is increasing or decreasing. So again, we need to start by finding our critical values for this function. So here we can take f prime of x using the quotient rule. We would have the derivative of our numerator is 1 times the denominator, x squared plus 1. Then we subtract the numerator, x, times the derivative of the denominator, 2x. And then divide by our denominator, x squared plus 1, quantity squared. Or simplifying a little bit, we're left with 1 minus x squared for our numerator, divided by x squared plus 1, quantity squared. So to determine the critical values, we first ask ourselves, is there anywhere that this function is undefined? And at first we might suspect, well, there's some x values where maybe we have division by 0, but recall that x squared plus 1 is always greater than or equal to 1, because any number squared has to be either positive or 0. So if I'm adding 1 to that quantity, then I have something which is greater than or equal to 1. So I can never have division by 0 here. So this derivative is defined everywhere. So the only way that I can have critical points is if I set my derivative equal to 0. And the only way that a fraction, or this quotient, can be 0 is if our numerator, 1 minus x squared, is 0. So it follows that x squared is 1 and x is plus or minus 1. So we have these two critical values, which will partition our domain of this function, the real line, into 3 subintervals. And we need to determine the sign of the derivative in each of these subintervals to see whether our function is increasing or decreasing on those intervals. So starting to the left of negative 1, we could choose as a test value x equals negative 2. And then we want to substitute that into our derivative to determine whether it's positive or negative. So to make our work a little bit easier when we substitute into f prime, let's consider our denominator first. So here, our denominator was x squared plus 1, and then that entire quantity is being squared. Now remember, when you square a value, you always get a non-negative number. Or in the case that we have x squared plus 1 being squared, we will always have a strictly positive number. Our denominator for the derivative is always positive, so all we really care about is the sign of the numerator. That will determine the sign of the quotient itself. So if we took x equals negative 2 and plugged into our numerator, we would have 1 minus 4, which is negative. So our function will be decreasing from negative infinity to negative 1. Between negative 1 and positive 1, we could choose 0. If we plug in 0 for x in our numerator, we're left with a positive 1. So our function would be increasing on that interval. And then to the right of 1, we could choose a test value of x equals 2. And again, our numerator would be -3. Therefore, the ratio is negative and our function is decreasing. So in part A, we have shown that our function is increasing on the interval from -1 to +1 and decreasing on the intervals -∞ to -1 or from 1 to infinity. Now in part B, we're asked to find the local extrema of this function, which we can use the first derivative test to find. So in part A, we had shown that our function changed from decreasing to increasing at -1, so it's bottoming out at -1. So we will have a local minimum at x equals -1, and to determine the local minimum value, we need to plug in -1 for x in our original function, f of x, because that's the function we're considering the graph of. So if we plug in -1 for x, we get a -1/2. And in part A, we saw that our function was changing from increasing to decreasing at x equals 1. So we have a local maximum at x equals 1. And to determine the local maximum value, we substitute 1 into our original function for x, and we have a +1/2 as our local maximum. So let's look at some other ones. In this next example, we have the same sort of problem, but working with a different function. Here, f of x is 1 minus x times e to the x. And in part A, we're asked to determine where this function is increasing or decreasing. So again, we start by finding the derivative of this function, f prime of x. So we start with the derivative of 1, which is 0. And then we have minus x times e to the x. So we've got a product, which means we have to make use of the product rule to differentiate. Now the product rule says we first differentiate the first function in our product. So the derivative of -x would be -1. And then we multiply by the second function in our product, which was e to the x. So we have -1 e to the x. And then we add the product of the first function in our product, which was -x, and the derivative of the second function, e to the x. Now the derivative of e to the x is e to the x, so we're left with the following, or if we simplify a little bit, we can factor out an e to the x from each term, and we're left with -1 minus x. So to find critical values, we first ask if there's anywhere that this derivative is undefined. And here we have the product of an exponential and a linear function. So these are both defined for all values of x. So the only critical values we could have are values of x such that this derivative is 0. So we have two options here. Either e to the x could equal 0, which is impossible. Remember, e to the x is always a positive number. So we're left with the expression in parentheses, -1 minus x has to equal 0, and so x would have to equal -1. So this critical value will partition the domain of our function, so here all real numbers, into two subintervals, everything to the left of -1 or everything to the right of -1. And to determine where our function is increasing or decreasing, we'll choose test values of x in each of these intervals and determine the sign of our derivative. So to the left of -1, we could take x equals -2. And when we substitute into our derivative, well, this e to the x term we said is always positive. And then we would have a -1 minus -2, or plus 2, would give us a positive value. So to the left of -1, our function is increasing. And to the right of -1, we could choose a test value of x equals 0. And plugging into our derivative, we would have e to the 0 is 1 times a -1 would be negative. So our function is decreasing from -1 to infinity. So stating our answer, we say our function is increasing on the interval -infinity to -1 and is decreasing on the interval from -1 to positive infinity. So in part B, we ask for the local extrema of the function f. And in part A, we saw that there was only one critical value where we were changing from an increasing function to a decreasing function. So the first derivative test says that we have a local maximum at that x value of -1. And to get the local maximum value, we substitute -1 into the original function, which would give us a 1 plus 1 times e to the -1 power, or if you prefer, 1 plus 1 over e. So we have a local maximum at that critical point, and there is no local minimum. There was no other critical point, and recall that the theorem we had seen earlier said if a function has a local extremum at some point, it must be a critical point. So let's look at some other ones. In this next example, we have the function x minus the natural log of absolute value x. And we're asked to find the intervals on which this function is increasing or decreasing. So as with our previous examples, we start by finding the derivative of our function, f prime of x, which would be 1 minus the derivative of natural log absolute value x is 1 over x. And to determine critical values, we ask ourselves, well, is there any point for which this function is undefined? We know that we can't have division by 0. So here, x equals 0. We might ask, or might assume, is a critical point. But one tricky thing for this example, remember that a critical value, or a critical point for a function, was a point where the function itself is defined, but maybe the derivative isn't, or the derivative is 0. Now, in this example, x equals 0 would make our derivative undefined. However, if we look at the original function, x minus the natural log of x, well, the natural logarithm, or any logarithm, can only be defined for positive numbers. Therefore, we could not take x equal to 0. The natural log of 0 is undefined. So 0 is not a critical point here, or a critical value, because the original function is not defined at that value. However, we still want to consider if our function would change from increasing to decreasing at that point, since our function would be undefined there. Now, the other critical points that we could have would be if our derivative is equal to 0, which would mean that 1 is equal to 1 over x, or x is equal to 1. So x equals 0 and 1 are going to be our points of interest here. And if we sketch the domain of this function, that is all real numbers except 0, because remember the log of 0 is undefined, then we also have a critical point at x equals 1, and our domain is partitioned into these three subintervals. So we have to determine whether our function is increasing or decreasing on each subinterval, we need to choose test values. So for a number to the left of 0, we could take -1, and substituting into our derivative, we would have 1 minus 1 over -1. So 1 minus a -1 would give us a positive 2. So our function will be increasing from -infinity to 0. Between 0 and 1, we could choose a test value of 1/2. Substituting 1/2 into the derivative, we have 1 minus 1 divided by 1/2, or 1 minus 2, which gives us a -1. Our function would be decreasing on that interval. And choosing a value of x to the right of 1, say 2, substituting into our derivative, we would have 1 minus 1/2, which is a positive 1/2. So our function will be increasing. So in summary, our function is increasing on the intervals -infinity to 0, or from 1 to infinity, and is decreasing on the interval from 0 to 1. Now in part B, we're asked to find the local extrema of f. And based off the work that we had done in part A, we saw that our function was changing from an increasing function to a decreasing function at 0. So we might initially expect that we have a local maximum at 0. However, recall that our function is undefined at 0. That is, there's a hole, or possibly an asymptote, in the graph of our function. So here, since the function is undefined there, we have a local maximum which does not exist. That is, there is no local maximum for this function. And we would have a local minimum at the value where we changed from decreasing to increasing, namely at x equals 1. And to get our local minimum value, we would evaluate the original function at x equals 1. So that would give us 1 minus the natural log of 1, which is 0. So we're left with just 1 for the value of f at 1. All right. So in the last part of this section, we'll consider the same sort of problems which we've already been looking at, but with some sort of application. So in this example, we're told the total revenue in billions for Procter & Gamble Company can be approximated for the years 2000 to 2015 by the revenue function r of x is the polynomial given here, where x equals 10 corresponds to the year 2010. So in part A, we're asked to determine in what year did the revenue have a local maximum. So there's a couple of ways we could look at this problem. When we see that question about a local maximum, we might try to determine where our function has a, or where it's increasing or decreasing, and make use of the first derivative test. So we start by looking at the derivative of our revenue function, that is marginal revenue, which would be negative 2.2x plus 27. And we ask first, is there anywhere that this function is undefined? In this case, no, since it's a polynomial. So the only critical values we could have are if we set this derivative equal to 0. And so solving for x, we would have 2.2x is equal to 27. So x is then 27 divided by 2.2. which is approximately 12.27. Since the value of x equals 10 corresponded to the year 2010 in the problem statement, this x equals 12.27 would be somewhere in the year 2012. Now, the question is, well, we found this critical value for x, but how do we know that it yields a local maximum and not a local minimum? Well, we could make use of the first derivative test. So if we consider the x-axis here, so our timeline, we found that we had a critical value of x that was approximately 12.27. And if we choose a test value of x to the left and right, say to the left of 12.27, we could choose a simply 12. And substituting into the value of our derivative, we find that we would have a positive number. Whereas if we take a number to the right of 12.27, maybe 13, and substitute into our marginal revenue, we get a negative number, so revenue would be decreasing on that interval. So we see from the first derivative test that we would have a maximum at that time. So here we could say in the year 2012, this revenue function would be maximized, have a local maximum. Now, perhaps an easier approach in this particular example is if we notice that our revenue function, r of x, is a quadratic polynomial. We can recall from our Chapter 3 material that the graph of a quadratic is a parabola. And here, since the coefficient for x squared was a negative 1.1, that means it is a parabola opening downward. So wherever that maximum or wherever that critical point occurs, where we had a derivative of 0, must be a maximum. And we could even find the value of x without relying on the derivative if we recall that the vertex of a parabola occurs at the x value given by negative b over 2 times a. So here we would have a negative 27 divided by a negative 2.2, or the two negatives would cancel. We have a positive 27 over 2.2, which was the same value that we found by using the derivative. Now, in part B of the problem, we're asked what was the maximum revenue. So to determine the actual local maximum value, we're going to take our critical value for x, which was 12.27 approximately, and substitute it into our original function for revenue. So rounding to the nearest billion, we find that this is approximately $85 billion was the maximum revenue in that part of 2012. So in our last example, let's consider modeling or a function that represents, say, the number of people infected with some disease after an epidemic begins. So perfect example considering the coronavirus pandemic. So here, let's suppose that the number of people, P of t, measured in thousands, which are infected t days after the beginning of some epidemic, is approximated by this function. 10 natural log of 0.19t plus 1 divided by 0.19t plus 1. And the question is, for this function, when will the number of people who are infected start to decline? So we need to know where this function p of t is decreasing. That is, where its derivative is negative. So we'll start by finding our derivative. So here, looking at the function p of t, we see that it is a quotient of two functions, so we're going to have to make use of the quotient rule. And our numerator involves the natural log of a polynomial. So we're also going to have to use the chain rule to differentiate the numerator. So let's start there. The quotient rule says we first differentiate the numerator. So we would have 10 times the derivative of the natural log of a function is given by the derivative of the inner function, so in this case 0.19, divided by the inner function itself, 0.19t plus 1. So that is the derivative of our numerator using the chain rule. And then we multiply by the denominator, which was 0.19t plus 1. Then we subtract the product of the numerator, which is 10 natural log of 0.19t plus 1, times the derivative of our denominator, which would be 0.19. And then the entire expression is divided by our denominator, 0.19t plus 1 squared. So simplifying a little bit, in the numerator, we see when we have this division by 0.19t plus 1, and then we're multiplying by that same expression, those terms will cancel. And so we're just left with 10 times 0.19, which gives us 1.9. Then we're subtracting. Let's see the rest of this. We had a 10 times 0.19, which again gives us 1.9, and then times the natural log of 0.19t plus 1, all over our same denominator, 0.19t plus 1 quantity squared. So to determine when the number of people infected starts to decline, we want to know where this function is decreasing or where this derivative that we just found would be less than 0. So to determine the sign of our derivative, let's think about this. Our denominator, 0.19t plus 1, when we square it, will always be positive. So the denominator is always positive, which means that our sign of the derivative is determined only by the numerator. So we can say here that our derivative, p prime of t, will be negative if and only if our numerator, which was 1.9, minus 1.9 times the natural log of 0.19t plus 1 is less than 0. So solving this inequality, we have 1.9 would have to be less than 1.9 times the natural log of 0.19t plus 1. So dividing both sides by 1.9, we're left with 1 is less than the natural log of 0.19t plus 1. And then to eliminate the natural logarithm, we could exponentiate both sides using a base of e. So we would have on our left-hand side, e to the first is less than 0.19t plus 1. So subtracting 1 from both sides, we have e minus 1 is less than 0.19t, and therefore t would have to be greater than e minus 1 divided by 0.19. So making use of a calculator to find the expression on this left-hand side, we find that this value is approximately 9. So here, the number of days that have passed t would have to be greater than 9, approximately. So we could say after approximately 9 days.